please explain the difference in the capabilities of this telescope versus what we've had previously?
Yeah, so first of all, it's all that. And the excitement was in part because so much could have gone wrong with this thing. And the fact that nothing went wrong, we were ecstatic. So one of the great challenges that we face is, how do you put a telescope in orbit that's bigger than the rocket that's going to launch it? Is that even possible? And the Hubble telescope, do you know what set the size of that 94-inch diameter mirror? That's the biggest mirror you could fit in the payload of the space shuttle.
Oh.
That's what set the size of that telescope. Big as it was, we would have made it bigger if the space shuttle were bigger. The value of the Hubble was that you could update it with servicing missions, and it was serviced many times. Here's the thing. So notice the Hubble telescope, its diameter is the spherical shape that fits in the spherical payload of the space shuttle. So now we want to put a bigger telescope into orbit. How do you do that? And so this is where you need engineers, clever engineers. Here's a rocket, one of the most powerful rockets we can use, but the fairing, that's the place where you hold the payload, can only be so big. And they say, all right, why don't we fold the telescope? Now, how are you going to fold the mirror? Oh, you turn the mirror into segments, hexagons, and you slip that into a fairing, and then you launch it 1,000,000 miles from Earth, opposite the sun from Earth, and it unfurls like petals of a flower. And it has a unique set of baffles that shield it from sunlight, so that the mirror and the detector can be very, very cold, because it's specially tuned to observe infrared that comes to us from space. And infrared, as you may know, we normally associate it with heat. Well, how am I going to detect something that's very, very cold in space if my detector is hotter than what I'm trying to detect? There's no way to see something that is warmer than the temperature of your detector. So your detector has to be very cold. So these are the baffles. They're many, many layers, so that when sunlight hits one layer, that layer absorbs it and re-radiates it in both directions, forward and back. So there's less that goes to the next layer. So then the next layer re-radiates it, and by the time it gets to the fourth layer, hardly anything goes towards the telescope. And so it's insulated, and it drops to deep space cold temperatures. It's specifically tuned for the infrared part of the spectrum. You remember the spectrum, so you have like visible light, Roy G. Biv, right? If you want to remember it, red, orange, yellow, green, blue, indigo, violet. Those are the parts of the spectrum we can see. But there's light outside of this. There's like beyond the violet, there's ultraviolet. That's how you get that. And below the red is infrared, not visible to the human eye. The earliest forming galaxies in the universe radiated a lot of ultraviolet. So you might say, well, let's get an ultraviolet telescope. No, because 14 billion years later, the expansion of the universe has redshift